Hello, good afternoon. Can you hear me? Hello?
Yes, yes.
Can you hear me?
Yeah.
Oh, okay, good. Good afternoon.
Hello,
yeah,
sir.
So I'm sorry that last time there was some internet problem. So I'm going to start where I left off last time.
Okay.
I mean, till the point where people could hear it, I'm going to assume that that is all done. So I'm going to redo some of the things which you might not have seen last time because of the internet problem. There was a serious problem. You could not see anything at the end. Okay, anyway, so let's start. So this is a small result which says that
Sir, we cannot hear you. Hello, sir, are you there?
So I'll do it from my desktop.
Okay.
Yeah. Hello, can you hear me now?
Yes, sir.
Yes.
Okay, so I'm going to restart. Let's see. I have to somehow get rid of this. So I have to share my screen. But I've not prepared this here, so I don't know how it's going to work. Let's see. Just wait. Okay. So I have to share some other screen. You see, there's some problem with my iPad. It's the microphone is not working, it seems. You could not hear the voice, right?
Yes, but now it's fine.
Now it's fine, but that's the iMac and I don't have the slides in the iMac. So let's see, let's try still.
Are they in your Dropbox?
Yes, but you know, the slides are in different format, so I
Ah,
don't have the
okay,
time
okay.
to
Okay.
do the right thing. So let me see. Still, we will try to manage somehow today. Something I don't know what is wrong with the iPad. It should not be like this. Okay, just a moment. Okay, so I believe should be somewhere here. Yeah. Mhm. Okay, so I'm going to share my screen now. Let's see. Share screen. I think it's this one here. So you can see the screen now?
Yes, sir.
Okay.
Yes, yes.
I believe that it's not as good as it was on the laptop, but still I believe you can read what is there on the screen, right?
Yes.
Okay, okay. So let's continue from here. So what this proposition says is that this raising to the power p map here takes un into un plus 1, and it induces an isomorphism of groups from un modulo un plus 1 to un plus 1 modulo un plus 2. Okay. So here's the proof. What I have to show is that if I have an x in un, then x to the power p is going to be in un plus 1. But if this x is not in un plus 1, then x to the p is not in un plus 2. That's what will make this map injective. You see? And if have I already proved that un modulo un plus 1 is a cyclic group of order p? I have already proved that, right? I think we have done it already. So what will result from this injectivity is that it's actually an isomorphism, because these two are groups of cyclic groups of order p. Okay. So how do I show that if x is in un, then x to the power p is in un plus 1? So you just compute, you write x equal to 1 plus p to the n times a, where a is in zp. You can write x like this because x is in un. Every element of un is congruent to 1 modulo p to the n. So if it is of the form 1 plus p to the n times some a in zp. Now I just use the binomial theorem to compute x to the power p, which is 1 plus p to the n times a whole to the power p. So you have this binomial expansion here, right? And I've suppressed some of the terms. The middle terms here are have been suppressed because they are all divisible by p to the 2n plus 1. So if I want to see what this thing is, modulo p to the n plus 2, I can ignore terms which are divisible by powers higher than n plus 2. And these middle terms are divisible by p to the 2n plus 1. That's because the binomial coefficient itself is divisible by what? It's divisible by p. The plus 1 comes from there, and so you get this. So also my n has been so chosen that np is strictly greater than n plus 1. That's why I took my n to be greater than 1 if p is equal to 2, right? So yeah, here it is. So you will get x to the power p is congruent to 1 plus p to the n plus 1 times a modulo p to the n plus 2. Okay. So this shows that x to the power p is in un plus 1, but not in un plus 2, if x is not in un plus 2. If x is not in un plus 1, right? If x is not in un plus 1, then this a is not congruent to 0 mod p, and therefore this x to the power p is not in un plus 2. Okay. So that's what you get this isomorphism of un modulo un plus 1 to un plus 1 modulo un plus 2. Okay, so here is another way of saying the same thing. You have the stop map, which is raising to the power p, takes un to un plus 1, and it takes un plus 1 to un plus 2. So it induces a map on the quotients. And this map on the quotients, the bottom map here is an isomorphism. Okay. So that's a small, it's a very useful observation. Yes, so I had not yet, right. So we are going to use it here in this next proposition already. So what does this say? That if I have an n which is strictly positive, or is strictly greater than 1 if p is equal to 2, and r is any integer which is strictly positive, then the group un modulo un plus r is cyclic of order p to the r. It's a cyclic group of the appropriate order p to the r. So it doesn't depend upon n. Okay. So if I have to go show that some group is cyclic of order p to the r, I have to find an element which generates the group and which has order p to the r. Okay. So I'm trying an x in un. So any x, for example, any x will do, right, which is not in un plus 1, such as take 1 plus p to the n. 1 plus p to the n is not in un plus 1 because it's not congruent to 0 modulo p to the n plus 1. It's congruent, I mean, it's not congruent to 1 modulo p to the n plus 1. It's congruent to 1 only modulo p to the n. That's the highest power.
That's good.
So now we repeatedly apply the previous lemma, and we will get x to the p to the I is in un plus I. Okay? But it's not in un plus I plus 1. So what does that mean? If I denote by xr, the image of x in un modulo un plus r, then xr to the power p to the r minus 1 is not equal to 1, whereas xr to the power p to the r is equal to 1. Okay, so xr has power p to the r. So I have found an element of order p to the r. Now I have to show that it generates the whole group. Okay, which group? I want to show that it generates the group un modulo un plus r. And one way of showing that it generates the whole group is to show that this group has order p to the r. Okay, that is what I'm going to do. So what is the order of this group? This group un modulo un plus r, it is a subgroup which is un plus 1 modulo un plus r, which is a subgroup all the way down up to the trivial group un plus r modulo un plus r. All the way. So I've given this sequence of, maybe it's, how many of them are there? R subgroups or something? Right. The first one has index p in the whole group. That is because of this isomorphism. The second one has index p in the third one. The third one has index P in the second one. The fourth one has index P in the third one, and so on, all the way up to the trivial group, which is the rth in the sequence. So the order of the group is P to the R. Okay. So we have shown two things. If I take an X which is in UN but not in UN plus 1, then its order is P to the R. Its order in what? In UN modulo UN plus R. I should say the order of its image in UN modulo UN plus R is P to the R. That's one thing. The other thing I've shown is that the order of this group UN modulo UN plus R is also P to the R. Okay? So that's that was this. Now, you see, these are very small things which I'll not go into great detail. Let me explain what's going on in a few words. So this one here, this 95, it simply amounts to saying that if I have a cyclic group of order P to the R and an element of that cyclic group, then there's a unique map from Z modulo P to the R to that cyclic group, taking 1 to that element. Here is the condition. So I had chosen an X in UN. I'm denoted by XR, the image of X in UN modulo UN plus R here. So that's a generator of this group. And I'm saying that whenever I have a cyclic group of order P to the R, there's a unique map from Z modulo P to the RZ to that cyclic group, taking 1 to your chosen generator. So that's the statement here. And therefore, there's nothing to prove, really. The other thing is to notice is you look at this diagram here. You forget about what is written. Just look at this square, okay? So the vertical arrow, you can recognize what it is. It's part of the inverse system we had used to define ZP, right? The projection from Z modulo P to the R plus 1 Z to Z modulo P to the R Z. This is something that you can see. Similarly, you have this map from UN modulo UN plus R plus 1 to UN modulo UN plus R. Why is this map there? This map is there because this UN plus R plus 1 is contained in UN plus R. Okay? So this group here has a subgroup which is UN plus R modulo UN plus R plus 1. And when I go modulo that subgroup, I get this group here. And that's the quotient map here. So I have this isomorphism of cyclic groups at the bottom and the isomorphism of cyclic groups of order P to the R plus 1 at the top. This sends X to XR plus 1. Here at the bottom, it sends, not X, 1. The element 1, the generator on the left, is sent to the generator XR plus 1. And here, the generator 1 is being sent to the generator XR. And this diagram commutes. Okay, so all this is being done to get an isomorphism from the inverse limit of these things on the left, which is ZP by definition, and the inverse limit of these things on the right, which is UN. This one has to check. There's a small amount of checking involved, that if I take some UN, go modulo U to the N plus 1, then I have a map from UN modulo U N plus 2 and a map from UN modulo U N plus 3 and so on. I get an inverse system. And the inverse limit of that system is just UN. Okay? And so the upshot of all this is that whenever I choose an element x in UN, I get a map, a homomorphism from ZP to UN, taking 1 to x, and that homomorphism is an isomorphism if x is not in UN plus 1. Okay, so that is the structure of this group UN. You can always choose an element x which is not in UN plus 1, and then I get an isomorphism with ZP by sending 1, which sends 1 to that element x. Okay. Okay, so here is, let's look at this number 99. So it first says that if P is different from 2, then U1 is isomorphic to ZP. We have shown it for all UN, and N was allowed to be equal to 1 when P is odd. N is not allowed to be equal to 1 when P is equal to 2. You have to take N equal to N strictly greater than 1. We'll come to that. But we just look at, so U1 we have shown is isomorphic to ZP. And here itself it says that if P is equal to 2, then U2 is isomorphic to Z2. And what is U1 in the case P equal to 2? It's isomorphic to, first of all, it is the whole of Z2 star. When P is different from 2, U1 is different from ZP star. Because the quotient of ZP star modulo U1 is FP star. But when P is equal to 2, F2 star is the trivial group. It just has one element, right? The element 1. So Z2 star is equal to U1, and it's Z star, which is plus minus 1 times U2. Okay, so about P odd, we have nothing to prove. We have already proved everything. We just have to do it for P equal to 2. So we have to show that Z2 star is Z star times U2. So let's take an element in Z2 star. You can uniquely write it as plus minus, S is plus minus U, where U is in U2, right? Why can you do it? Because every X in Z2 star will go to either plus 1 or minus 1 modulo 4. What is Z2 modulo 4? Star. That's plus minus 1. So if I take an X in Z2 star, it'll be congruent to plus minus 1 modulo 4. So that is your S. And if I multiply X by S, then I get an element which is congruent to 1 modulo 4, and that's the U that you take. Okay. So now there are some remarks about these quadratic characters we had introduced last time, lambda p plus and so on. There's another way of looking at them. Let's ignore this and come to 101, which says that I'll just use the notation Gn for Z modulo p to the n Z star. This ring Z modulo p to the n Z, it was being called An in the first 2 lectures. The group of units of that ring, I'm going to call it Gn. This is just in order to make things easier to write. This is an abbreviation. So now we want to determine the structure of this group Gn. What does this group look like? So, what does it mean to determine the structure? So, one thing is to say that, okay, write it down as a sum of, direct sum of cyclic groups, for example. That's what you can do to any finite commutative group. This is Gn is a finite commutative group. And every finite commutative group can be written as a sum of cyclic groups, and you know a certain uniqueness which goes with this decomposition. We will not need that uniqueness part, but let's just try to write it as a sum of cyclic groups. Okay, so the proposition here, 1 or 2, says that if P is odd and take any n strictly positive, then of course from Gn I have this surjection to Fp star, right? It says that it has a canonical section, and Gn is canonically isomorphic to this Fp star times U1 modulo Un. Remember that U1 modulo Un is cyclic of order P to the n minus 1. This is what we have proved here for, yeah, where is it? Un modulo Un plus R is cyclic of order P to the R. So U1 modulo Un, where is it? Yeah, here it is. Un modulo Un, U1 modulo Un is cyclic of order P to the n minus 1. Yeah, here it's written here. It's written here. And it is generated by 1 plus P. Right? That's what we had proved. You take any element in U1 which is not in U2, and that's going to be a generator of this quotient. So what is Gn? By definition, it is you see Zp star, and then you have the kernel Un. I mean, you have the map from Zp star to Gn. It's surjective, and the kernel is Un. So Gn is really equal to Zp star modulo Un. And we know the structure of Zp star. So Zp star is what? Fp star times U1. And this Un is contained in U1. And U1 modulo Un is cyclic of order P to the n minus 1. So that's it. We just had to show that Gn is isomorphic to this Fp star times U1 modulo Un. Okay. So, I mean, here is something basic, Z modulo P to the n Z star. It is a statement about the ring Z, or the group of units of one of its quotients. And it's easiest to prove using Zp. This Zp proof we have given is among the easiest. Of course, you can prove it more directly as well. So what happens for P equal to 2? Here you have to take an n which is strictly greater than 1. And then you have this map from Gn to G4, right? Gn, what is Gn? It is Z modulo 2 to the n star. And if n is greater than 1, then you have a map to G4 star, G4. And this is a canonical section. So Gn is isomorphic to Z star, which is just plus minus 1, times U2 modulo Un. And this U2 modulo Un, we have seen, it's cyclic of order 2 to the n minus 2. And it's generated by any element such as 1 plus 4. Well, I mean, this is 5, such as the element 5, which is not contained in U3. You could not take 9 as a generator. You can take 5 as a generator because it's congruent to 1 modulo 4, but not congruent to 1 modulo 8. 9 would be congruent to 1 modulo 8, and that won't do as a generator of Un modulo U2 modulo Un. So it's the same proof. Okay. So let's look at this exact sequence. What does it say? You have your Gn, which is Z modulo P to the n star. It surjects onto Fp star, and the kernel is Un modulo U1 modulo Un. Okay. Okay, so what did we show? We showed that this exact sequence has a section. It's an exact sequence of commutative groups. And here is another more elementary direct proof that such a sequence has a section. So what's the statement? The statement is the following. It says that if I have a short exact sequence, 0 to A to E to B to 0, of finite commutative groups, and the orders little a and little b of the groups capital A and capital B are relatively prime. Their GCD is equal to 1. So the statement is going to be that not only does such a sequence have a section, but essentially there's a unique section. So here is what the exact statement is. Says that if I take B prime to be the set of X in E killed by little b, then this B prime is a subgroup of E, and E is the internal direct sum of A and B prime. What does internal direct sum mean? So in a commutative group, if you have two subgroups, so the big group is, let's say G, and the subgroups are H and K, you say that this commutative group G is the internal direct sum of H and K if the intersection of H and K is trivial, and every element of G can be written as a sum of an element of H and an element of K. Or in other words, if you equivalently, you could simply say every element of G can be uniquely written as a sum of an element of H and an element of K. Okay, so that's what internal direct sum means. And so the statement is that B prime is a subgroup and E is the internal direct sum of A and B prime. Moreover, B prime is the only subgroup of E which is isomorphic to B. That's the uniqueness part that I was alluding to, right? That essentially there's just one section. Okay, so how do we prove this lemma? Of course, it's a purely algebraic lemma. Now, I'm given that A and B are the GCD is equal to 1, right? So there are elements R and S in Z such that AR plus BS is equal to 1. Now, if I have to show this intersection A intersection B prime is trivial. So if I take an X in the intersection, then AX is 0. Why? Because the element X is in capital A, and BX is also 0 because capital B prime is defined to be the set of elements such that BX is 0, right here. So AX is 0 and BX is 0. So AR plus BS times X, which is equal to X because AR plus BS is equal to 1, whether that also has to be 0, and therefore this intersection is trivial. Okay. So next, observe that B times every element of capital B is trivial because this capital B has order little b. Therefore, B times E is going to be contained in capital A. And therefore, BS times X is contained in A for every X in E, right? If B times every element is contained in A, then B times Sx will also be contained in A, right? Also, AB times E is 0 because AB is the order of E, and it follows that ARX is in B prime for every X in E. So you try to figure out why it follows from this that ABE is equal to 0. it follows that ARX is in B prime. Yeah, because B prime is the set of those elements which are killed by little b, right here. And this element here will be killed by little b because of this condition. Okay, so this element here is in B prime. Okay, ARX is in B prime for every x in E. So BSX is in A and ARX is in B prime. But every x can be written as ARX plus BSX because AR plus BS is equal to 1. So every element of E can be written as an element of A plus an element of B prime. And therefore, I've proved the two things which are required to show that A is the internal direct sum, not A. E is the internal direct sum of A and B prime. Okay. Okay. So, of course, when you have an internal direct sum and you restrict this projection A going to B prime, then you get an isomorphism, right? These things are equivalent, obviously. That A and B prime are supplementary, as they are sometimes called. That's the same as saying that the restriction of this projection to B prime is an isomorphism. Okay. Now the second part was saying that if I have any subgroup of B prime of A, which is isomorphic to B, then it has to be equal to B prime. So let's take some subgroup B double prime, which is isomorphic to B. Then of course, little b will kill every element of B double prime because little b kills every element of capital B, right? So this B double prime will be contained in B prime because B prime consists of all elements which are killed by little b. And they have the same number of elements, therefore they have to be equal. Okay. Okay. So here is something very, very, this statement 107, let's come to that. It says that if I have an element A in ZP star, a unit in ZP, then I have this map raising to the power A. It's a map from UN to UN, and it's an isomorphism of groups. Okay, one way of seeing this is that, what have we proved? We have proved that UN is a ZP module of rank 1. It's written multiplicatively. We had shown that it is isomorphic to ZP, right? Where is it gone? It was a consequence of, yeah, here it is. So we get an isomorphism of ZP with UN. So if you have any ring A and any A module M, then every invertible element of this ring A gives you an automorphism of the module M. Multiplication by an invertible element is of course invertible because you just multiply by the inverse to get back to where you were, right? So that's what is being said here, nothing very profound. So once you have made UN into a ZP module, then of course every unit in ZP gives you an isomorphism or automorphism of this ZP module. The only thing which is not standard here is that usually you write modules over a ring additively. You don't write them multiplicatively. But here these UNs are naturally multiplicative groups. They are subgroups of the multiplicative group of ZP. So we continue to write them multiplicatively. So scalar multiplication is sort of exponentiation. The notation here is essentially what would be scalar multiplication if we were looking at modules written additively. Okay, so then I'm going to stop for 2 minutes to see if you have any questions. Otherwise, we go on to the next thing, which is to discuss QP, the field QP, right? So are there any questions? Okay, there are no questions. Then we can continue with QP. Okay. So first of all, what is QP? By definition, it's just the field of fractions of Z.
Sir?
Yes? Yeah.
Sir?
Yes, yes.
Sir, how these powers of A is defined? I mean, in the previous slide
Right. Okay, so one
for
simple
A in GP.
right. Yeah. One simple way of thinking of it is as I said, okay, the simplest way of thinking of it is to say that after all, this UN, here it is a ZP module. Okay, so I believe that we should go back to this thing about let's look at this isomorphism. Where was it? Here it is. Yeah, here. So let's look at UN modulo UN plus R, right? We had shown that this is isomorphic to, it's a cyclic group of order P to the R. So, and if I take an element X in UN, which is not in UN plus 1, then its image is a generator of this cyclic group. In other words, there's a unique map which sends 1 to that generator. What does it send the other elements of Z modulo P to the R Z to? It sends the element 2 to X squared. It sends the element 3 to X cubed, and so on. So, you see here, this group here is being considered as a module over this ring. And normally, when you have a module over a ring, you write scalars, you multiply by scalars. Because the module, the group law in the module is written as addition. But if it's written as multiplication, as here, you have to write your scalar multiplication, you have to use the exponential notation as here. Okay? So similarly, my, here it is. Here, my module UN, it's a module over ZP. But UN is not written additively, it's written multiplicatively. So multiplying by a scalar means, I mean, the notation is raising it to the power A. And this exponential notation comes from the exponential notation at the various finite stages, as I've indicated before, right? So if you are still wondering what this exponentiation means, then as in everything, you can understand it in terms of periodic expansions. So elements of UN will look like 1 plus A1 times P to the N plus A2 times P to the N plus 1, and so on. The elements of A, I mean, this A is in mean, you can exponentiate, you can raise an element of un to any power in ZP, not just in ZP star, right? It's being said that when it is in ZP star, it's an automorphism, it's an isomorphism. But it makes sense for any element of ZP. So that element A also has a periodic expansion. So you truncate the element of the periodic expansion of X, you truncate the periodic expansion of A, and then you just have natural numbers. And of course, you can raise natural numbers to some power. Excuse me, I got a cold. Anyway, so, and their exponentiation makes sense. And that gives you the periodic expansion of the powers. So basically, it comes from the fact that UN is a ZP module and it's written multiplicatively. So scalar multiplication is written as exponentiation. Any other questions? So let me just wait for 2 more minutes to see if people have questions.
So here we are just saying that if there is like a sequence of modules mi, where each mi is an Ri module, then the inverse limit of mi will be an module over the inverse limit of Ri. Right?
Yeah, sorry, could you repeat the question?
So here we're just using that if you have a inverse system of modules like mi.
Yes. Yes, go on. You are perhaps the right thing. So
but not
I have an
modules,
inverse
but
system
abelian
of
groups.
rings,
So
of which ZP is the limit.
Yeah.
And I have an inverse system of modules over each of these rings. So the inverse limit of this inverse system of modules is going to be a module over the inverse limit of the inverse system of rings.
Yeah.
That's what you were trying to say, right?
Yes. Yeah.
That's correct. That's correct. That's the way to think about it. Yes.
But sir, I mean, if these rings don't have any relation among them, then how can you define these maps in that inverse system in the first place?
The maps in which inverse system? In the inverse system of rings or the inverse system of modules?
So you are telling that mi is an Ri module for each I, right? But
Sorry,
then,
say it again.
So I mean, the setup was that each mi is an Ri module for
Yes.
each I.
Yes.
So I mean, what are the maps between these modules when these two base rings are different?
It will not be a module map, just an abelian group map. I mean, this is an inverse system of abelian groups, I think.
Okay, it's an abelian group. Okay.
But the maps like Ri cross mi to mi, these maps should commute with
that's right.
With the morphisms.
Yes. So I don't know whether I have this diagram somewhere. Maybe I should have drawn this diagram, and I can't do it because my iPad is not working. But okay, so let me try to explain it in words. So you have an inverse system of rings. Let's say A2 going to A1, A3 going to A2, A4 going to A3, and so on. That's the inverse system at the bottom, let's say. On top of this, I have an inverse system of modules. So Mi is a module over Ai. So I have a homomorphism of groups from Mi plus 1 to Mi. But so it should be a homomorphism of Ai plus 1 modules, because Mi plus 1 is a module over Ai plus 1, and so is Mi, because Mi can be viewed as an Ai plus 1 module through Ai. It's an Ai module, but Ai is a quotient of, there's a map from Ai plus 1 to Ai. So I can view Ai modules as Ai plus 1 modules. Okay? And so you should have this kind of compatible homomorphisms between these modules. Then the inverse limit of the modules is going to be a module over the inverse limit of the rings. Right. Okay. So let's come to this field QP. Now this is a very, it's very easy to define in terms of ZP. The first definition is that it's just the field of fractions of ZP. So every element of QP is A by B, where A is in ZP, B is in ZP, and B is not 0. Okay. And because every X in ZP, different from 0, can be uniquely written as P to the M times U, where M is some natural number and U is a unit, QP can also be thought of as ZP, in which you have inverted P. So you see, the field of fractions is obtained by inverting every non-zero element. But here, it's enough to invert just one non-zero element, namely P. Because once you've inverted P, every other element gets automatically inverted. For example, this X will get inverted because if P is inversible, then, and U is also invertible, of course. Inversible is French, invertible in English. So if P is invertible, then of course P to the M is invertible and U is also invertible. So X is going to become invertible in QP. If, I mean, I've inverted P in QP, right? So one of the immediate consequences of this fact that is that every X in QP, non-zero, can be uniquely written as a power of P, but the exponent is now allowed to be an arbitrary integer instead of just being a positive integer as here for ZP. So every X can be written as P to the M times U, where U is invertible in ZP and M is an arbitrary integer. So earlier, if you remember, we had defined VP to be this exponent M. And we extend this definition now to the whole of QP. So for every element of QP, VP of X is the power of, I mean, of course, for X equal to 0, you put VP equal to plus infinity, right? But for every non-zero element, X, it's the power of P in this decomposition. It's the exponent here, which is VP of this X, okay? This U should be invertible in ZP star, so ZP, yeah. So what do you get? I mean, this VP becomes it's a morphism. I mean, okay, this is a fancy way of saying, okay, let me just say it in the fancy way. It says it's a morphism from the multiplicative monoid QP to the additive monoid Z union plus infinity. So all that means is that VP of X plus Y is, not X plus Y, excuse me, VP of X times Y is VP of X plus VP of Y for every XY in QP. And of course, the convention is that VP of 0 is plus infinity and N plus infinity is equal to plus infinity for every N in Z union plus infinity. So that's the usual convention about adding this plus infinity to a number, right? So that's just the first property of this VP. It's so easy that doesn't even require a proof. I mean, you just write your X and Y in like this. If X is P to the M times U and Y is P to the N times V, then XY is of course going to be P to the M plus N times UV, and UV is going to be invertible. So VP of XY is going to be, VP of XY is going to be M plus N, right? And that's it. But this VP is also a valuation in the following sense. That's very important. So what it says is that VP of X plus Y, VP of the sum of two p-adic numbers, elements of QP are called p-adic numbers as opposed to p-adic integers, which are elements of ZP. So the VP of the sum of two p-adic numbers is at least, I mean, it's greater than the VP of X and the VP of Y. It's greater than both of them. So it's greater than the smaller of those two. No, it's greater than the smaller of those two. It could be equal to one of, anyway. So what you have is that if these two are different, then you actually have equality. So when I said it's greater than both of them, that's not true. What is true is that it's greater than the smaller of those two. That's what this says. And you actually have equality in this when these two have different valuations. So VP of X is called the valuation of X, the p-adic valuation to be more precise, right? So if the p-adic valuation of X is 2 and the p-adic valuation of Y is 3, then the p-adic valuation of X plus Y is going to be equal to 2. Okay? So that's the p-adic valuation. Then there's this thing called the p-adic absolute value of nx, of a p-adic number x. So that is defined as you just raise p to the power minus vp of x. So here, notice that there's a minus sign, which is very important. So for example, if x is equal to p, what is its p-adic absolute value? It's 1 upon p. If x is p squared, the absolute value is 1 upon p squared, which is smaller. If x is p cubed, then the absolute value is 1 upon p cubed, which is even smaller, and so on. Whereas the absolute value of 1 upon p is equal to p. Okay? So this one has to be careful about. This is slightly counterintuitive if you are only familiar with the real absolute value, where you tend to think of a number having greater absolute value as being, in some sense, bigger. Here, what the absolute value tells you is how divisible the number is by p. The more divisible it is, smaller its absolute value is. If it's divisible by p squared, then the absolute value is 1 upon p squared. I mean, if it is exactly divisible by p squared, right? And not by p cubed. Anyway, so this absolute value, it's a homomorphism from this to positive reals, and it satisfies this inequality. Where does this come from? This inequality here, it's a direct consequence of this one here, and the definition, of course. You combine the definition and this inequality of valuations, you get this inequality of absolute values. And the convention is that the absolute value of 0 is, of course, 0. So in this inequality, you have equality if these two absolute values, there's a typo here. This plus should be a comma. I mean, of course, it's not. This plus should be a comma. So the absolute value of a plus b is smaller than the bigger of these two absolute values. Okay? It's not a plus. If it's a plus, then there's no need to write sup. So anyway. Okay, so you have equality. And then once you have an absolute value, you actually can define a distance, a p-adic distance dp between the points of your space qp. The p-adic distance between x and y is the absolute value of the difference x minus y. Okay, so this inequality here can be translated in terms of the distance to this inequality here. And this is called the ultrametric inequality, or it's called the strong triangle inequality. So when you have the usual distance on a metric space, one of the requirements, of course, it should be symmetric and I know it's positive and whatever. But the main thing is that it should satisfy the triangle inequality. So the distance from x to z should be less than the distance from x to y plus the distance from y to z. That's the usual triangle inequality, what I've just said. But here, this satisfies a stronger triangle inequality. Not only is this periodic distance from x to z smaller than the sum, it's actually smaller than the bigger of these two. It's smaller than the bigger of these two. Okay. So that's the notion of the periodic distance between 2 points of QP. And so now QP is of course a ZP module, right? I mean, if you have a ring and you take its commutative integral ring and you take its field of fractions, then that field of fractions is a module over the ring. And you can consider submodules of that module. So basically what it is saying is that QP has all these submodules generated by these powers of P. And P to the m plus 1 is contained in ZP. So you have this chain of submodules, right? Each one of them generated by a power of P. And the bigger the power, the smaller the ideal, of course. Submodules of QP are also called ideals sometimes. I mean, certainly when there are submodules of ZP, they are called ideals. And in the case of QP, they are called fractional ideals. So the bigger the power of P which generates that ideal, the smaller is the ideal. Of course, that's because a bigger power has fewer multiples than a smaller power. And so you get this sequence of ideals, which extends in both directions to infinity. And the union of all these things is QP, okay? The union of all these things is yeah, that's right. Why did it say just m tends to minus 1? I mean, you have to take m in both directions. I mean, you take the union over all m and not just, yeah, so ignore this here. If you take the union over all m of these ideals PM ZP, then that's equal to QP. Okay, so here are some topological properties of this field. So the first thing is that QP is locally compact. As a metric space, it's complete for this distance dp. And the subring Z 1 over P. Z is a subring of QP, it's a subring of ZP. So it's a subring of QP. And when I invert 1 over P, it is still a subring of QP because 1 over P is there in QP. And it's being said that this is dense in QP. This ring is dense in QP. Okay. So from our first lecture, maybe we recall that ZP is compact. And as a subspace of QP, it's defined, you just check that it's defined by this condition. So in terms of VP, it's defined by the condition that VP of an element X in QP belongs to ZP if and only if VP of X is positive. VP of X can be positive or negative, it's an integer. If it's positive, then that element is in ZP. So if you translate that in terms of the distance, then that's what it comes to. So it's an open ball. ZP is an open ball in QP, and it's compact. So we have found a compact neighborhood of 0. But for any other point in QP, you just translate this neighborhood to that point, and you get a compact neighborhood of that point. So you got this, so QP is locally compact. And this is a general statement that, any locally compact group is complete. Okay, so QP is complete for this distance. So this actually is the definition for some people of QP. What they do is they start with the field Q, and on Q itself, they define this distance dp. How can you define it on Q itself? Because you can define this Vp on Q. You just write an element of Q. Where is it? Just a moment. Here. So you write your x is in Q now. You write your x as p to the m times u, but you just require u to be prime to p now. Of course, every element in x in QP or QP star can be uniquely written as p to the some integer power m times an element u, which is prime to p. And you declare this m to be Vp of x. So that defines a valuation on Q, the p-adic valuation on Q, and because it satisfies this inequality, then that allows you to define an absolute value as here, the same formula, but everything is for Q now, and then you get this distance on Q called the p-adic distance between 2 points of Q. And then you just complete Q for that distance and define QP to be the completion of Q for the p-adic distance. So that's another approach, and most people more inclined towards analysis will prefer this approach. We have taken a somewhat more algebraic approach where we have defined ZP as a projective limit, and then QP as the field of fractions of ZP. But of course, the two things are equivalent. They come to the same thing. Okay. And this ring is dense in QP. Okay. So why is that? So here's the statement. So one way of seeing it is that, yeah, that's right. One way of seeing that this ring Z1/P is dense in QP is to use p-adic expansions. This p-adic expansion here, I don't know why I'm getting this. Yeah. Anyway, so every element X in QP can be written uniquely as a formal form, as a power series in powers of P, but now some of the coefficients are allowed to be negative. It starts at Vp of X, and then the powers of P keep on increasing, but Vp of X can be negative. So just as elements of ZP can have a p-adic expansion, and the powers of P there are all positive, for QP, you allow some of the powers to be negative. The negative powers are only finitely many in number in any p-adic expansion of a p-adic number. So, and then if you take the partial sums, they are in ZP. And of course, that element X of QP is the limit of these partial sums. So every element X in QP is a limit of a sequence of elements in Z 1 over P. So that's dense in QP. Okay. So here is a definition of a uniformizer.
Sir, how did you say that any locally compact abelian group is complete?
Yeah, so I mean, that's a theorem in general topology into which I'm not going to go. I mean, it's there in Bourbaki, for example. If you
Okay.
yeah.
So, okay, I understand that Q to QP is another completion and they have the same means from Q to QP is a completion of Q with respect to the periodic norm.
Yes.
So from that way it is means I just wanted to see means both are equivalent. So
So what is equivalent to what?
means okay, if I take QP as a quotient of means quotient field of ZP,
Okay.
and then we have periodic norm there.
Mhm.
Okay, so what I'm saying is that QP already has periodic norm, and with okay, no,
Yeah, so
sorry.
that's right. Of course, maybe what you wanted to say is that if you define it as the completion of Q for the periodic absolute value or the periodic distance, then you don't have to prove completeness. But since I have not defined it as the completion, I have to prove. I've defined it in some other way as the field of fractions of ZP. So I have to prove that it's complete. And I'm just using the fact that it's locally compact to say that it's complete. Right?
Yes.
Okay. So here is a word which is often used. It says that an element pi in QP is called a uniformizer. So this is not your usual pi, of course, right? I mean, the pi in the real world, I mean, pi is just an arbitrary element of QP. It's going to be called a uniformizer if its valuation is equal to 1. If its periodic valuation is equal to 1. For example, you could take pi equal to p itself, right? Now you have this exact sequence. ZP star going to QP star going to Z going to 0. What is this map here? Sometimes people don't write the maps, but you have to see, you have to know what the map is. Here the map is just the inclusion of ZP star in QP star. But what is the map here? Is the map VP. That's the valuation. It takes QP star to Z. So I'm saying that if I choose a uniformizer, then I get a splitting of this exact sequence. What is a splitting? Of course, you all know that whenever, I hope you know that when you have an exact sequence like this, a splitting is a map from Z to QP star, which has a property that when you start at Z, apply that map, and then apply this projection, you get back the identity map of Z. So why do I get a section or a splitting whenever I choose a uniformizer of QP? Because a uniformizer of QP pi is an element here which goes to 1 here. And whenever I have an element of some arbitrary group, there's a unique homomorphism from Z to that group, sending 1 to the chosen element. So if I have a uniformizer, then I can send 1 to that uniformizer and I get a map, which is actually a map of groups, which is actually a section, right? And so once I have a section of this exact sequence, I get an isomorphism of Z cross ZP star, Z cross ZP star with QP star. So let's pause for a moment to compare QP to Q. Q star, what is the structure of Q star? Can somebody just quickly remind me what the structure is? Yeah, who wants to tell me what Q star, the structure of the group Q star is?
free abelian group generated by the prime?
Sorry?
The free abelian group generated by prime numbers?
So q minus 0.
Hmm. That's not the structure, that's the definition of Q star. What does Q star as a group look like? Is it cyclic of order 2, for example? No. So that is this. So the structure of Q star is that it's the product of a cyclic group of order 2 consisting of plus minus 1 and then a group which is a direct sum of infinitely many copies of Z indexed by the prime numbers. Essentially, I'm restating the fact that that there is unique factorization in Z. That the ring Z is factorial. Every element of Q can be uniquely written, Q star can be uniquely written as plus minus and then a product of primes. So, okay. So recall that, you know, that was the structure of Q star. That's very complicated. You have a direct sum of infinitely many copies of Z indexed by the prime numbers and then a cyclic group of order 2. Whereas for QP star, you have just one copy of Z, one copy of Z. But of course, the units of Z, which were just plus minus 1, and the units of QP star of ZP star are more complicated. ZP star is more complicated than plus minus 1, but this part is simpler in the case of QP. Okay, anyway, so this is the structure. You get an isomorphism like this whenever you choose a uniformizer of the field QP. Okay, now what we have also determined the structure of ZP star, right? This was the structure of ZP star for P different from 2. And this was the structure of Z2 star. It was isomorphic to Z star, which is just plus minus 1, times U2, recall U2, but that was isomorphic to Z2. And in the case of P odd, ZP star was isomorphic to FP star times U1, and U1 was isomorphic to ZP. So you get this wonderfully complete description of QP star. It's just Z times FP star, which is cyclic of order P minus 1. I hope you all know this, right? What is the structure of the multiplicative group of FP? What is the structure of FP star? It's a cyclic group of order P minus 1. And a generator is called a primitive root in the old terminology. So you know the structure of Z, of course, you know the structure of FP star. And then ZP, I mean, you know the structure of ZP as well. I mean, it's just the inverse limit of Z modulo P to the n Zs. Okay, so that was for P odd, but for P equal to 2, you have this slightly different kind of a thing. You have this Z star factor, which is extra when P is 2. Okay, so if I know the structure of QP star, then I can compute what QP star modulo squares is. And that's good. If P is odd, then it just consists of 4 elements. It's a group of order 4. Of course, it's not the cyclic group of order 4, because this is a group of exponent 2. Does everybody understand the terminology exponent 2? Yeah, I hope you do. So basically, if I take an element of QP star, U, let's say, or in fact, U is in ZP star, I take an element of ZP star such that lambda P of U is 1. What was lambda p? I'll just recall it briefly. Lambda p is the map from you go from zp star to fp star, right? Fp star is a quotient of zp star, but I mean you obtain it by going modulo u1, and from fp star you go to plus minus 1 by sending the squares in fp star to 1 and the non-squares to minus 1. That's called the Legendre symbol sometimes, and it's also perhaps called so the squares are called quadratic residues and the non-squares are called non-residues and so on. I mean, it's just, that's very old and terminology, but basically you are just looking at things which are squares and not squares, and that's your lambda p. So if you choose an element u in zp star such that lambda p of u is minus 1, which just means that u is not a square. I could have written here u in zp star, but not in zp star squares. Then these 4 elements, 1, the image of u, the image of p, and the image of u times p. These 4 elements constitute this group qp star modulo squares. That's very simple. If I had q here instead of qp, what is q star modulo q star squares? Now here is a question which somebody should be able to answer. What is the group q star modulo squares? What is the structure of this group? Okay, so you think about it. It's not very complicated. Once you know what q star looks like, you should be able to tell what q star modulo squares looks like. But it's certainly a much more complicated group than this group of 4 elements. For one thing, it's an infinite group, q star modulo squares. So basically it's a group of square-free integers or something like that. Okay, so here we had to leave out 2. Now what is q2 star modulo squares? This is a slightly more complicated group. It has not just 4 but 8 elements. And the 8 elements are, of course, you just have the 4 elements of z2 star modulo squares. This we had determined earlier. Last time we determined this, right? What is Z2 modulo squares? And then in addition to this, you have this 2, so which also gives rise to these 4 elements. These are the elements which are there exactly in Z2 modulo squares. Of course, that has to be a subgroup of this, right? This here is a subgroup of this. Namely, this part here. This is the same as this. And then you have these 4 elements, which, so it's a subgroup of index 2, and the other coset consists of these multiples of 2, so to speak. So that's it. So we have determined the structure of QP star modulo squares. Now recall, what is this VP? It's a map from QP star to Z. So when I take -1 to the power VP of X, I call it new P of X. That's going to be a map from QP star to ±1. And of course, it's a surjective map because, for example, I take X equal to P, then VP of X is going to be 1, and -1 to the power 1 is going to be -1. So new P is a surjection from QP star to Z star. So such surjections have been calling quadratic characters, right? From any group whatsoever, a surjection to Z star is a quadratic character of that group. So this new P now is a quadratic character of QP or QP star. QP star. But now if I choose a uniformizer of QP, right? A uniformizer is just an element which has valuation 1. Then whenever I have a uniformizer, I get a map from QP star to ZP star as well. Not only do I get a section here, but I also get what is called a retraction here. A retraction in a short exact sequence is a map from the middle thing to the first thing, such that when I start at the middle thing, go to the first thing and come back to the middle thing, I get the identity map of the middle thing. Just wait a moment. Is that what? So that's for a section, for retraction, you'll have to, no, that of course, that's not what it is. What it is the following. You start at the first thing, you go to the middle thing, then you apply that retraction, you get the identity map of this thing. Okay? A section is something different. A section is a map from the last thing to the middle thing, such that when I start with the last thing, apply the section first, and then apply this projection, I get the identity map of this last thing. A retraction is something where you first apply the given map, and then you apply the retraction, and you should get the identity map of this first thing. So whenever I have choose a uniformizer, I get a sort of retraction of this inclusion. Here, the word is used here, retraction. It means that any X in ZP star will go to itself under this retraction. Okay. So once you get a retraction, I mean, it's a map from QP star to ZP star, I can view quadratic characters of ZP star as quadratic characters of QP star. Any map from ZP star to something else can be viewed as a map from QP star to that thing, because I've got a map from QP star to ZP star. So in particular, if I have a quadratic character of ZP star, I get quadratic characters of QP star, and those ones are going to be called ramified quadratic characters of QP star. Okay, so basically for P odd, there are basically 3 quadratic characters of QP star. They are nu P, lambda P, and the product of these two things. And they are determined by, here is a small matrix giving the values of these quadratic characters on a system of generators, basically, of QP star modulo squares. QP star modulo squares, because squares are killed by any quadratic character, right? A quadratic character is a map into a group of exponent 2. It's a map into plus minus 1. And the square of any element in that group of plus 1 and of minus 1 is, of course, 1. So quadratic characters of QP star are nu P and lambda P. They are killed. They kill the squares. So I just need to tell you what the values of these quadratic characters on U and P are, what these values are, and they are given by this matrix. Similarly, for Q2, I have 3 quadratic characters. One quadratic character nu2, which I called the unramified quadratic character. And these other 2, which are the ramified ones, they come from Z2 star. And this matrix gives you the values of these quadratic characters on this basis of Q2 star modulo squares. So I'll stop here today. I wonder whether the connection is still on. I mean, can you still hear me? Hello?
Yes, sir, we can.
Yeah, okay. So I'll stop here. It's fortunately the connection, although it was unstable, it was still, sorry.
So,
Hello, is there a question?
Ganesh,
या ऐसा करिए जो रोटी खाई ले तो रोटी फिर के भीतर रख देना
अच्छा
थोड़ी सी एक टुकड़ा खाई जाए
एक काम करो गणेश 10 की गोली ले आना मेडिकल पे 10 की गोली ले मेडिकल पे
Okay,
10
so
की गोली
I've finished for today.
तीन ले लो मैं गोल पे कर दे रहा हूँ
And
रिंकू भैया 10 रुपए दे दी मैं गोल पे कर दूंगा
okay, so I'm ending the meeting and we'll meet on Monday. And there's a tutorial on Friday at 3 o'clock in the afternoon. Okay, bye.